Welcome back to Science Click. Today, how to visualize general relativity. The goal of this video is to show different representations of the theory and to put forward a brand new one, which I have not yet encountered, although it possesses a great number of qualities. The idea behind this new representation is to make the best possible use of the video format, and in particular its temporal dimension, in order to faithfully reproduce what the mathematics tell us. In middle school and then high school, we learn that free fall can be modelled by a force. It's the force of gravity. This force allows us to predict the movement of objects, stating that they are attracted to each other, and in particular to massive objects like the Earth. However, this description is merely an approximation, and it fails when the pull is too strong, such as the path of Mercury around the Sun. It was in 1915 that Albert Einstein proposed a new theory, a rigorous mathematical model which made it possible to describe freefall more accurately. For Einstein, there is no such thing as a force that would act at a distance. It is the fabric of the universe itself which gets distorted and drags objects into a fall. In order to grasp this very complex theory, it is important to design visualizations that make it more intuitive. The representation that is most often used is that of a large elastic sheet on which massive objects are placed. By deforming the fabric under their weight, the more massive objects pull everything in their direction, like marbles in a bowl. At first, this image seems to have two advantages. It is very simple and intuitive, and it helps us understand that bodies attract each other indirectly, through an underlying fabric, space-time, whose geometry can be altered. However, although it is extremely widespread, this way of presenting general relativity has a large number of problems, which make it not very rigorous. In this video, we will try to improve this image by making 4 major changes. To begin with, the image of the elastic sheet seems to indicate that objects are placed on space-time, like marbles, while in reality, space-time is the fabric of the universe that contains them. Therefore, one improvement that we can start with is to flatten objects onto the surface, so that it is clear that they are not exterior but contained within space-time. Next, one of the biggest problems with this representation is that it sort of explains gravity by gravity. To the question, why does the apple fall on Earth? This visualization seems to answer that it is because the apple is pulled downwards, which causes it to fall like a marble in a bowl. But it is not acceptable to explain gravity inside space-time, using gravity outside space-time. We hence have to find a better explanation. In particular, it is more rigorous to say that if objects follow the well created by the Earth, it is because they move in a straight line but within a curved geometry. When they fall, objects move straight ahead, but the curvature of space-time gives us the impression that these trajectories are deflected. To understand, we can imagine the surface of a sphere, on which 2 ants would head north. At the start, the 2 paths are parallel, and we might think that as they progress straight ahead, the 2 trajectories will never cross. However, the 2 ants end up meeting at the North Pole. This is possible thanks to the curved geometry of the sphere, on which straight lines tend to get closer to one another. Inside space-time, the phenomenon is similar, and objects seem to attract each other when they are simply following the curved geometry in straight lines. However, this picture of an elastic sheet is still misleading. Indeed, one could think that if space-time can bend, it is due to the existence of a higher dimension. Here, for example, the 2-dimensional sheet seems to bend into a 3rd dimension. In reality, this is not the case, and the mathematics of relativity do not require any higher dimension for the universe to bend. It is therefore preferable not to represent this sheet seen from the side, but rather from the top, with a grid to illustrate the curvature.
While we're here, this also allows us to restore the 3 dimensions of space in which we live.
Finally, the most important issue with this representation is the fact that our diagram completely ignores the time dimension. Space-time is an object with 4 dimensions, 3 dimensions of space, but also 1 dimension of time, which can equally bend and curve.
Faithfully rendering a 4-dimensional geometry is strictly impossible, and we therefore have to find a trick.
A first idea would be to add small clocks to our diagram at each point of the grid. In this way, the space grid becomes a space-time grid, and we understand that time can flow differently depending on where we are. That being said, adding clocks to our diagram doesn't give us much more intuition, and in particular we still don't really understand what causes objects to fall.
If we drop an apple, for example, why does it start to move towards the Earth?
To really understand, it is necessary to remove 1 dimension of space to represent the dimension of time. In fact, it is the time component of the curvature which explains gravity. With such a diagram, we see that the apple is always in motion. Even when it has no speed at the start of its fall, the apple is still moving in time. It progresses towards the future. When no force is applied to the apple, the curvature of spacetime will gradually bend its trajectory between a temporal speed towards the future and a spatial speed towards the ground. The apple moves in a straight line, but the curvature of spacetime rotates the orientation of this straight line between time and space. We therefore understand that if the apple falls towards the ground, it is because it started with a speed through time. The curvature of spacetime generated by the Earth has merely converted this temporal speed into a spatial speed. Having said that, as human beings, we do not perceive the temporal speed of objects. When an apple is dropped, it appears to us to be motionless. We do not perceive the fact that it has a motion through time. From our point of view, we experience the world instant after instant. And this diagram where objects form tubes over time, world lines, is not very intuitive. Our last step will therefore be to slice this diagram, to cut it up instant by instant, in order to form an animation which includes time. The curvature of the universe, which causes straight lines to dive into the Earth, becomes a movement of contraction. The rate of this contraction is constant and perpetual because the curvature of space-time, which depends only on the mass of the Earth, is always the same.
However, it is very important to understand that the geometry does not really contract. It's the fact that straight lines get closer together that gives this impression of contraction.
The phenomenon is quite similar on the surface of a sphere. The curvature is constant on the sphere, but the straight lines seem to be perpetually getting closer together. It is this representation which I find to be the most appealing for visualizing general relativity. The Earth, because it is very massive, deformed spacetime, giving it a curvature.
For us, the curvature of spacetime appears as an endless contraction of the grid.
In technical terms, we say that the volume contained between geodesics shrinks over time because of the curvature.
This grid that shrinks represents what we call inertial frames.
Frames in freefall. With respect to this grid, a body that is not subject to any force will conserve its movement. Thus, if we drop the apple with no initial velocity, as no force acts upon it, it will remain motionless relative to the grid, but as the grid contracts, the apple will fall. With this image of relativity, it is also easy to see that the surface of the planet is constantly accelerating upwards, because it is always going against the natural movement of the grid. Finally, if we throw an object sideways with an initial velocity, no force is applied on it, and it will therefore continue in a straight line within the grid. But as the grid contracts, the object is constantly pulled back towards the Earth.
That's exactly how the Moon orbits the Earth, and the Earth orbits the Sun.